So today we have the speaker from Luis Garcia from Rutgers. And as many of you know, one of the themes that we try to exploit wherever we can in the research that we do in CredC is that energy delivery systems are different from enterprise systems in that sometimes you have a that describes what they should be doing, and you're able to maybe collect some other measurements or get some other source of information that lets you assess whether or not a particular device or subsystem is behaving according to how it is being instructed to behave and also according to the physical models. And you can leverage the physics, as our sponsor likes to say, to inform the security, and this can be either for detecting or preventing. And so Luis is going to tell us about some of the ways that, I don't know how well, okay, he's going to tell us how attackers can leverage the physical models, okay. PLC is a programmable logic controller. It's sort of a generic term used to describe kind of the endpoint field devices in electrical substations or also in, for example, oil and gas refinery and pipelines. In other words, not the control room computers, but something that's actually affecting a circuit or turning a valve. And without any further introduction, Luis, it's all yours. Yeah. Please mute unless you have a question.
Sorry?
Oh, you can go ahead, Luis.
All right, well, thank you for the introduction. Yes, so my name is Luis Garcia. I'm a third-year PhD student in the ECE department at Rutgers University. I'm working under the tutelage of Dr. Saman Zanous in his Forensics Cybersecurity and Forensics Research Lab. And yes, as he mentioned, I will be presenting our work in leveraging physical models for both attacking and defending PLCs. Just to provide a quick outline, I'm just going to provide some background information, and then we'll discuss Harvey, which is a model-aware rootkit that leverages the physics of the system. And then we'll discuss our current work in device-oriented verification of cyber-physical systems, and then we'll conclude. So I know a lot of us here are familiar with programmable logic controllers and industrial control systems, but I figured I'd give a refresher just in case. So in this industrial control system, at the top you'd have the management level, which may contain the SCADA center, or supervisory control and data acquisition, for monitoring the entire system. And this would interface with the network components of the control level, which would also contain the PLC and the human-machine interface. And these would be interfacing with the field-level devices, which are actuating and sensing on the physical system. And what is a programmable logic controller? As you mentioned, the way we view it is it's the interface between cyber and physical components in many CPS applications. And it contains simple logic code that's typically easy to verify. And they're usually the target in cyber-physical systems attacks. For example, Stuxnet, which I'm sure everyone here is familiar with, but we'll go into detail on it a little bit. And to provide an overview of the PLC architecture, at the top we'd have what we call the virtual world, and this consists of the industrial control system network components and as well as the human-machine interface. And this interface is with the PLC, which has an application layer called the control logic that sits on top of the firmware, which interfaces with the hardware. And then the hardware interfaces with both the sensing and actuation of the physical world. And essentially, the sensor measurements are sent through the input of the hardware to the firmware and propagated through the control logic of the system. And the outputs are then forwarded back through the firmware to the hardware to the actuators of the physical world. And this is what we call the program scan cycle of a PLC. And to provide an example industrial control system, we consider a simple power grid network, in this case a 3-bus system with 2 synchronous generators. And we might consider that the red squares represent circuit breakers, and we can consider that you might have an intelligent electronic device, such as a PLC, opening and closing the circuit breakers on a transmission line. Then on top of this, you would have an HMI system, or for example, or a SCADA center that would monitor the PLC values and send actuation commands. And then you may have a programmer that could be air-gapped to the system that will be allowed to change the PLC configuration as well as the control logic that's loaded onto the PLCs. And these two connections typically have different access rights. Usually the programmer has the ability to change, as we mentioned, change the configuration and the control logic of the PLC, while the SCADA center usually only monitors and sends control commands. And as we mentioned before, there have been the cyber physical systems attacks on PLCs. One of the most popular is the Stuxnet. And I wanted to provide an overview of Stuxnet because I would like to later compare how it's different than the attack that will be presented in our today's presentation. So Stuxnet was an advanced malware worm that attacked Siemens F7 PLCs and WinCC systems, and it targeted high-frequency drives controlling centrifuges, and it caused billions of dollars in damages, and that's a very brief summary of Stuxnet. But going back to our ICS example, the network. Yes.
Yeah, can you help me make the difference between PLC and the remote terminal unit?
I'm sorry?
Can you help me understand the difference or the link between the PLC control and the remote terminal unit? You know.
Oh, well, in this case, we can, as we mentioned before, I mean, these are just, we're considering PLC as a general term in this case as just an intelligent electronic device that's actuating on the system, right? Just runs simple logic. So it could be, you know, it's kind of a category of devices in this case, but there are specific programmable logic controllers that are designed for specific purposes. So in this case, I'll go more into detail about the PLC that we use for our setup. So as I mentioned, so Stuxnet focuses on these two communication channels. And to provide, to continue with our overview of Stuxnet, so on the programmer's PC, you would have the Step 7 software that programs the control logic of the PLC, and you'll have a helper DLL file that actually takes the programming commands from the Step 7 software and converts it to the network commands that are sent to the PLC. And what Stuxnet did was it injected a custom DLL that sits and renamed the original DLL file so that it can sit as a man in the middle between the programming software and the original DLL file. And this allowed it to send malicious commands and propagate it to the PLC. And there have been prior efforts to mitigate the attacks like Stuxnet, and these are typically offline or passive solutions, and they're usually implemented as external solutions for PLCs. So in the first case, we have TSV, which is a Trusted Safety Verifier. This is a work that was done by our group in which it sits as it's a verification mechanism that sits between, as a bump in the wire between the PLC and the programming PC. And essentially, the PLC code is lifted, the instructions are lifted to an intermediate language that are then symbolically executed and verified against some safety specifications. And essentially, this provides a way of formally verifying the PLC code that's loaded onto the PLC. But again, this is an offline solution as you can't do real-time monitoring of the code. And in the second case, we have Reusable board, which is an intrusion detection solution that sits on the chassis of the PLC backplane and essentially monitors all the signals and communication going to and from all the modules of the PLC, so the processor, the communication modules, and the I/O modules. But again, this is a passive solution as it's just an intrusion detection solution. So this kind of segues into our work with Harvey, the modelware rootkit, and this was actually presented in our paper that has just been recently accepted to NDSS and will be presented at the end of February. So our paper was called Hey, My Malware Knows Physics, Attacking PLCs with Physical Modelware Rootkit. And this was a collaborative effort with the Technical University at Darmstadt as well as Florida International University. And so Harvey is a modelware rootkit that takes into account the physical topology of the industrial control system. It uses the physical models to optimize control commands for an adversarial objective function. And in order to implement Harvey, we assume that we can compromise the PLC's firmware. And there are multiple ways of doing this, the first being utilizing the firmware update mechanism to replace the firmware over the network with a custom image. We can also do local firmware modifications such as an SD card or JTAG implantation. When we say SD card, some of these PLCs can be store custom firmware images on the SD card, and you can program the PLC to flash the firmware every time you boot the PLC. And JTAG implantation essentially relies on a device that can implant JTAG commands to the JTAG port of, and we'll go into the JTAG explanation later, but essentially this was an attack shown by in a recent Black Hat presentation. And finally, we can rely on runtime attacks such as network exploits or remote code execution vulnerabilities. And there have been several presented as recently as 2016, such as Frosty URL. Now, the system model we consider has an operator that's interfacing with an HMI, and this HMI is interfacing with a central control system that's connected to a network of PLCs, and these PLCs are actuating and sensing on a physical system, which in this case we consider a power grid. And for our adversary model, we assume that the attack is stealthy. And the reason why we want a stealthy attack is because it's more enduring, as we see in Stuxnet. Now, we can easily develop this attack to just simply go in and break the PLC and render it useless. And this would cause damage, but it wouldn't have as enduring of an impact. And we also assume a PLC-only attack where we only assume that we compromise the PLC as opposed to compromising the programmer's PC and the HMI panel. And the reason why is because these platforms are usually protected by more complex defense solutions, and it's kind of outside of the scope of our paper, where we focus only on compromising the firmware of the actual PLC. And finally, we assume that we can extract the physical model. And this is a strong assumption, but as we've seen in the case of Stuxnet, the physical model can be extracted using insider information or assuming that there's an energy management system that contains information about the physical model. These systems can be compromised and can be used to extract the physical model. So now that we've presented the general idea of Harvey, we can discuss how it actually implements the two-way data manipulation. So at the top, we have the operator interfacing with the legitimate control logic, and we don't change any of the control logic on the application layer. The control logic will send legitimate control to the PLC firmware, and this is where Harvey rests, and it would take the legitimate control and use it to feed a benign model that generates fake legitimate looking measurements back to the legitimate control logic and propagate it to the operator. Then at the bottom side, we have the physical system that's sending the actual measurements from the sensors to the PLC firmware where Harvey rests, and Harvey is intercepting these measurements and using it to feed into a malicious model that will generate adversary optimal malicious control to the actuators. So that's the general overview of how Harvey works. And just to clarify, back to our ICS example, Stuxnet attacked these two communication channels, while our attack focuses on the interface between the PLC and its own I/O modules. And in order to implement Harvey, we actually had to select the device and specification, and we went with an Allen Bradley CompactLogix L1, which is based on TI's Stellaris LM3S2793 microcontroller, which is an ARM Cortex-M3 instruction set architecture. And the reason why we chose this device was not only because we had these PLCs in our lab, but also it's one of the more widely used PLCs in the industry now. And before we go into the attack, I wanted to first describe some of the components that are necessary for understanding the later demonstration. So first, I just wanted to point out the 16-bit digital inputs. So at the bottom we have the GPIO input ports, and at the top we have the blue LED strip that corresponds to the values of the GPIO ports. So if you have a high value in input port 0, then the 0 LED should be on. And when we say high value, we mean 24 volts DC, and low value will be about 8 volts DC. And similarly, we have a 16-bit digital output, and the green LEDs correspond to the GPIO-Output ports. So now that we have our PLC, we wanted to figure out a way of what aspects of the firmware we needed to update, we needed to change. So there have been prior works that reverse engineer the firmware update procedure of different Allen Bradley PLCs. And although they simply bricked the PLCs, they provided us with a means of updating the firmware. And we did spend a lot of time analyzing the firmware update procedures, but we found that we were not wasting time, but this wasn't our main contribution because it had already been done. So we wanted to focus on was, once we had this firmware update procedure compromised, what can we do with it? And so we essentially decided just to dump the memory and dump the firmware that's actually on the device, and this proved to be more efficient for our goals. So in order to do this, we needed to establish a JTAG connection, and JTAG is a Joint Test Action Group standard that's designed to assist with device, board, and system testing, diagnosis, and fault isolation. And it's usually the first approach used for reverse engineering efforts. So when we opened up the PLC, we first needed to identify where the JTAG ports were. And we had an idea that this, based on the architecture, that we identified that this is a JTAG port, but then we had to verify using the datasheet of the microcontroller which pins corresponded to the particular JTAG signals. And we used the multimeter to verify which one was connected to which port of the JTAG connection. And then we had to modify our JTAG adapter for our debugger, and we just used some wires to rewire some of the connections. And we were able to eventually establish a JTAG connection, and we used the JTAG interface to dump the memory for code disassembly. And another important note is that we had the data sheets for the microcontroller, and this allowed us to see how the memory was mapped. And it also allowed us to see the built-in ROM functions. And this provided us with a lot of necessary information, such as the mapping of the GPIO ports and so on. And so once we dumped the memory, we decided to do a static memory analysis. We figured that we should follow the boot sequence to determine the control flow of the program. And we used the notion that for the Cortex-M3 processors, the reset handler is located at address 4. And so once we found the reset handler, we loaded the memory image into IDAPRO, which is a multi-processor disassembler and debugger, and we decided to follow the boot sequence. So we would start at address 4, and I don't know if you can see it, but we see that at address 4, the reset address is E3, so we would go to E3, and from here there's a branch to a subroutine at address B8, and then once we see this subroutine, we would analyze what values are being modified, and the goal of this was to see where we can intercept the I/O communication. And although this was a brave approach, it obviously wasn't feasible, as there was so many different control flow paths that it would have been impossible to accomplish this in a reasonable amount of time. So because of this, we leveraged the fact that the PLC actually has a slow boot up sequence, and I actually have a little animation that shows the sequence. So whenever the PLC boots up, it just lights up all the LEDs, and we use the notion that the LEDs correspond to all the GPIO ports. So we figured that if we could figure out the memory address associated with the LED, we could essentially find it later on in the code and see where it was being modified, and this would lead us to where we can intercept the I/O communication. So essentially what we did was we halted the CPU during the boot up process, and then stepped through the execution to see where the LEDs were being written to, and we were able to step through this with the JTAG communication, and we were able to find that they led us to the interrupt service routines that were responsible for forwarding the GPIO values to and from the PLC. So the first function we're going to look at is actually the function that updates the GPIO outputs from memory. So these are the values that are taken from the application layer and are forwarded to the GPIO ports, to the hardware. So here we have the function entry, and at the top we have the address of the memory value that's taken from the application layer, and we have the address of the LED outputs. This is the values that this is the memory address that we found that corresponds to the LEDs. And so this section of code just stores the value from the application layer and registers associated with the LED output. And what this loop here does, it just changes the value from memory to a format that suits the GPIO ports. And once that value is calculated, it's forwarded to the GPIO output ports. Now, in order to implement our attack, we intercepted the control flow at the point where the value from memory is stored in the register whose value is manipulated in the loop. In this case, it was stored in register R5. Now, what we did was we injected a branch instruction at this point where the value is stored in R5, and we would branch to an arbitrary point in code, and here this is where we would branch to the point where we actually injected our code, and the code simply writes the mask value to R5, and this mask value can be whatever we want the GPIO ports to be, GPIO port values to be. And then once we write this mask value to R5, we can branch back to the subsequent instructions. And similarly, we also modified this interrupt service routine where we update the memory from the GPIO port. So we're essentially taking the values that are coming in from the hardware and forwarding them to the application layer that's propagated to the operator. And we did a similar attack where right after the GPIO port values are read, we would branch to injected code location, and then we would write a mask value to R5 and then branch back to the subsequent instructions. So for an example attack scenario, we developed a simple logic system where we have, if input ports 0 and 1 are high, then output port 1 is high. So this is just implementing a simple AND gate. And if input port 0 is low or input port 1 is low, then the output port 0 is high, which implements a NOR gate. So this system can represent a typical safety condition where we can say, okay, we can only start a process at output port 1 if two safety conditions, input port 0 and input port 1 are met. Otherwise, we are in an idle position, or we set output port 0 to high. So we developed the associated simple ladder logic program, and ladder logic is just the graphical programming language used to program the simple circuit diagrams of relay logic hardware. And the system on the right represents the aforementioned AND and NOR gates. And one important note is that we actually use the programming software to act as our HMI panel. And the reason we did this was because we didn't actually have an HMI panel in our lab. So but we did find that the software can actively monitor the values coming out of the PLC, and it uses the same communication channels as the HMI. So we consider this just for our test, we consider this our HMI. And we just want to reiterate too that the LEDs and the HMI read the updated values from the same memory addresses in memory. So for our first attack, we wanted to spoof inputs. So as you can see here, input ports 0 and 1 are high. So according to our system, output port 1 should be high because that's the AND gate. But if you look at the actual GPIO ports, there aren't any inputs connected. So we fooled the PLC into thinking that it actually had high values at input ports 0 and 1. And then for spoofing the outputs, in the first case, we attached the voltmeter to output port 0, and it shows a low voltage of 8.54 volts. However, you can see that the PLC believes that the indicator shows a high value for output port 0. And similarly, the voltage for output port 1 is read as high, 24 volts, but the LED indicator shows a low voltage. So now that we implemented our simple code, we wanted to present a more advanced code injection. In this case, we used a PID controller. So first, we compiled an open source PID controller code to determine the space constraints. We didn't have access to the proprietary PID ladder logic instructions that come with the programming software, and the code we used was not optimized or stripped in any way. And furthermore, the PID implementation the typical PID implementations may only implement the P or PI cases. In our case, we implemented all three components, the proportional, integral, and derivative components. And this is just kind of showing you almost a worst case scenario for a PID implementation in terms of size. And once we knew how large a worst case PID attack code would be, we also wanted to figure out how much memory we would have available to us for code injection. So we manually inspected the code to determine the available and reusable memory. When we say reusable, we refer to code that is inaccessible to the control flow of the code and can be overridden. So if there's some dynamic memory that's writable and is only used during the boot sequence, we can identify this as reusable code because it won't be touched by the normal control flow anymore. And available memory is just areas of memory that aren't being used at all. And finally, we found that the available and reusable memory were sufficient enough to implement the PID attack code. And as you can see, it's important to note that the PID attack code can be much leaner. And you can see that these are the built-in PID instructions that normally come with the PLC programming software, and they're significantly smaller than our PID attack code. And on the left, I actually highlighted the previous relay logic attack code that we developed earlier. So you get to see how there's a significant difference in the size. So once we developed this more advanced attack, we wanted to evaluate our attack on a smart grid testbed. And luckily we had access to the FIU smart grid testbed in Miami, Florida. So they allowed us to configure a custom system. In this case, we use a IEEE 9-bus power system with 3 synchronous machines. And this is just showing how, the network communication, the network setup. And this is a picture of the actual testbed. And these are just some grid, enumerating the grid control applications, such as state estimation, load shedding, wide area monitoring control, event analysis and disturbance recording, protection, and power flow. And these final 2 slides are just showing both the SCADA operations as well as a lab view diagram of the overall system. So now that we had our PID controller, we needed to design benign and malicious physical models in order to implement Harvey. And we need the benign model to generate the fake legitimate looking measurements, and the malicious model for the malicious actuation on the system. For the benign model, we use the benign optimal power flow. And this essentially uses optimal power flow equations of power grid to minimize the costs while ensuring safe operation. So we would choose for example, we would choose the minimum, we would choose the decision variables such that we minimize the load balance equations for both real and imaginary power with a safety constraint that we can't generate for a particular bus a certain amount of generation. Then on the other end, for the malicious optimal power flow, we modified the optimal power flow that maximizes the cost while disregarding safety constraints. So we essentially negated the previous benign optimal power flow and removed the safety constraints of the system. Now, in order to implement these OPF models, we use the PID controllers, and the calculated commands of the OPF models are used as set points to be maintained by inner loop PID controllers. And so Harvey maintains a benign and malicious PID controller and the associated set of variables. Now, for our first attack, we implemented a steady state system malicious attack. And in this case, we didn't use the malicious OPF model. We just repeated heavy load circuit opening and closing, so without loss of power system stability. So we essentially just open and close the circuit breaker of a transition line several times. And although the attack resulted in the system exceeding permissible limits, stability was maintained. And you can see there were significant disturbances in both the frequency and voltage magnitude. They did not exceed the permissible limits, but the AC voltage phase angle between generators 1 and 2, as well as the power measurements, did exceed their permissible limits. Then on the operator side, Harvey ran a parallel benign model to generate fake legitimate looking sensor measurements to the operators. And we found that this attack did cause minor perturbations due to equipment operational noise, but these can be attributed to typical perturbations that are normally observed. And we should also note that this is dependent on the benign model that's used. So depending on how complex you make your benign model, you can do a trade-off between efficiency and complexity. So the second attack we implemented was the adversary optimal control attack. In this case, we used the optimal malicious attack with the malicious OPF. And we removed the safety margin conditions. As we mentioned before, we replaced the cost minimization with maximization. And we predefined some stealthy conditions, such as not allowing a power generator to be disconnected from the rest of the power grid. And we set a nominal frequency reference of 62 hertz. So the frequency exceeded the permissible limit, and we saw instabilities in the voltage magnitude, the AC voltage phase angle, as well as the power. And then again, on the operator side, Harvey ran a benign OPF in parallel and sent fabricated measurements back to the HMI, and we observed similar perturbations. Now, the limitations of Harvey is that the first being that the current implementation relies on JTAG implantation. Now, this is a limitation because we assume that the attacker has physical access to the model, but as we mentioned before, it has been shown that the firmware update mechanisms can be compromised. So this wasn't our contribution. Our contribution assumes that the attack can be implemented. And the second limitation is that the accuracy of the physical models are limited to the amount of memory required by the implementations. And finally, for a distributed attack, the PLCs cannot rely on network communication. They would rely on sensing and actuating, such as a side channel attack. And in our paper, we did present some possible mitigation solutions for Harvey. The first being remote attestation, where you'd use a verifier to check the software integrity of the system, or similarly, you'd use a secure boot with a trusted platform module to verify the device by itself. And finally, we mentioned an external bump in the wire solution between the PLC and the physical plant that would monitor the sensor to PLC and PLC to actuator data streams. And this is actually a project that's being worked on by one of my colleagues in our team. And we did provide some responsible disclosure. We did provide responsible disclosure to Alan Bradley, and we notified him of the possible repercussions of the previously demonstrated firmware vulnerabilities. And the company did allow us to present our work at NDSS. So now that we presented an attack model that leverages the physics of the system, we can now discuss our current work that in which we are using device-oriented verification of cyber-physical models. And I first wanted to discuss hybrid systems modeling. This is a very broad topic, and just to provide an example of hybrid systems modeling, I present here a hybrid automata of a thermostat. And we can see that there are two discrete states for a heater, either off or on. And in each state, we describe the continuous evolution of the system, or the physics. And each state has a guard or a trigger that triggers the discrete transition between one state to the next. And you can see on the right how a typical evolution of the temperature would be, as well as the evolution of the physical state of the system. And hybrid systems modeling is an extremely broad topic, and I don't have time to cover most hybrid systems modeling, but I did want to present briefly an example of differential dynamic logic, which is what we use in some of our work. And this is a logic for specifying and verifying hybrid systems, in particular cyber-physical systems. And this was presented by Andre Platzer's group at Carnegie Mellon University. And for this example, we consider two trains that are sharing a track, and we want to make sure that the back train does not collide into the train in the front. And you might have so the position of the back train would be labeled as Z, and the position of the front train would be M, and the back train is traveling at a velocity V. So we want to, when we specify a safety property, we want to make sure that Z is always going to be less than or equal to M. And also for the precondition of the system, you would, in his case, it's defined as the velocity squared is less than or equal to 2 times the braking force times M minus Z. And in this case, we want, these are equations that are derived from the physics of the system that are necessary in order to prove the safety property of the system. And for the operational model, we describe this continuous evolution of the system in this, or that usually include the differential equations. And in this case, we say that Z prime, or the position of the train, is equal to velocity, and V prime is equal to acceleration. And then for the discrete evolution of the system, we have discrete assignments. In this case, we are assigning a random value to acceleration because we say that the conductor of the train in the back has the freedom to accelerate or decelerate as much as he wants, but as long as as long as the acceleration obeys the guard test. So here is just a test that ensures that the conductor will not accelerate beyond a certain magnitude. And this overall system together can be verified using a sequence calculus that I'm not presenting today, but there's a sequence calculus associated with differential dynamic logic and several tools available. It's in particular Chimera X that we use for verification. And so we wanted to apply the knowledge that we gained from differential dynamic logic to the power grid. And we started out with a simple the transient stability of the single machine infinite bus system. So we can consider that we have two devices. In this case, they could be any type of intelligent electronic device that are controlling the opening and closing of a circuit breaker on a transition line. And you have a synchronous machine that's connected to infinite bus. And typically the transient stability, there are several categories of stability, and in this case we wanted to consider the rotor angular stability and of the system. And the rotor angle is just the reference angle between the synchronous machine and the infinite bus. So this is typically modeled using the equal area criterion, where we plot the electrical output power and the mechanical input power against the rotor angle. And I don't have time to describe the swing equation in this case, but the takeaway from the equal area criterion is that it can be used to calculate both the critical clearing angle and the critical clearing time of a fault. So essentially we have two states, either faulted or non-faulted. And in the non-faulted case, you assume that there's stable operation, but when you introduce a fault, you have a critical clearing time where the fault must be cleared to ensure that the generator doesn't fall out of step. So we wanted to apply a more formal approach to both modeling and verifying, where we can integrate more complex cyber components. And we figured that we can use differential dynamic logic hybrid verification for this purpose. And so we defined two discrete states, faulted or non-faulted. And for our verification purposes, we made several simplifications. Although we did simplify the system, the simplifications weren't critical enough to affect the dynamics of the system. So we were able to generate this invariant region for this system, and the blue invariant region essentially represents the point where, and here we're plotting the rotor angle velocity and the rotor versus the rotor angle. And what this is essentially stating is that if the rotor angle velocity and the rotor angle are at the initial state start at any point in this blue region, then we can assure that stable operation. It will stay in this region of attraction. Now, we then decided to overlay the hybrid case with the faulted case, and the golden arcs represent how the system evolves during the faulted model. And what this represents is that what this essentially states is that if we start with the rotor angle velocity and the rotor angle within this blue region, and the fault is introduced, then we would evolve along the golden arcs. And as long as the fault is cleared before we exit this blue region, then we can ensure stable operation. And another important note is that we did neglect the dampening component of the system. So if we included the dampening component, it would converge to the center of the blue region. Now, this was just the hybrid program representation of the single machine and infinite bus, and these are just the initial init is just the initial state of the system, and then we have the control, which is the discrete assignment of the system, and in this case we're just assigning the acceleration of the rotor angle to the swing equation, and then we have a plant that defines how the system evolves and the continuous evolution of the system. And then we have the evolution domain constraints, which are just the truths that may remain true throughout the continuous evolution of the system. And finally, we have the safety requirements, where we say that the rotor angle must be less than or equal to a maximum constraint of the rotor angle that ensures that the generator won't fall out of step. And for our current and future work, we would like to extend this model. We actually submitted the SMIB transient stability verification to a conference, but we're looking to add on to it by including a model for a governor of a hydro power unit that incorporates more the actuation of the cyber devices. And this is just a model of a block diagram of a governor for a hydro power unit. And we're also working on cyber physical control flow integrity. And control flow integrity is typically used in software verification, where you're verifying that given certain inputs and outputs, there's a certain control flow that must be followed according to a control flow graph. And what we want to do is to incorporate the physics of the system. Because these are cyber physical devices, they're interfacing with the physical actuators of the system. Therefore, the physics of the system should change. So we want, in addition to verifying the software control flow integrity, we want to verify the cyber physical control flow integrity. And if there is any violation, if, for example, if a circuit breaker is open, it should change the physical dynamics of the system. And if it doesn't match the physical possibly a range, then we can raise a notification or an alert. So in conclusion, we presented Harvey, which is a PLC rootkit that implements a physics-aware man-in-the-middle attack against cyber-physical control systems. It damages the underlying physical system while providing the operators the exact view that they would expect to see following their commands. And we also presented a device-oriented verification of cyber-physical systems with a focus on electric power grid using differential dynamic logic. And thank you for your time, and I'm willing to take any questions.
First off, let's see, any questions? Okay, Wheatland in Illinois.
I probably come a little bit late, so for the first part of the talk on I think the work on that, because you mentioned that you can inject into some attacks into the PID control in order to modify the optimal power of analysis. The question is that, because my understanding that a PID control is more on the transient activities of the power system, while the optimal power of analysis is targeted on its steady state. So I'm just wondering why these two connected to each other, because one is attacking on its transient, but you're using the steady state analysis as an experimental evaluation. So I guess probably I missed something.
Well, yeah, we did use, so we did implement our attack just using the PID controllers, but we consider it as it's really just a template for a more advanced attack. And in this case, we considered just a PID as being central to malicious optimal powerful control. And yes, we do understand that the optimal power flow is usually done offline, but we just we wanted to determine the variables that would maximize the control variables that would maximize the effects of our attack, and then integrate that information into the design of our PID control.
Another question on slide 50.
Sure.
I need to understand which costs are you sometimes minimizing or maximizing. When you talk
50.
Oh, 50? Oh, sorry. Okay.
Yeah, I need to understand which costs are you minimizing or maximizing. There is a lot of cost in power grid that you can work on it. Which one are you talking about?
Yeah, so in this case, we're just minimizing the load balance equation. So just the generated power minus the consumed power. I mean, but again, it's really just a template, and any cost functions can be integrated depending on the physical models of the system.
Is the operator's only view an HMI into the compromised PLC, or does the operator have, for example, some auxiliary measure of system frequency?
In this case, we do consider that the only view of the PLC is from an HMI panel or any monitoring entity, so we don't assume that there's an auxiliary sensing device.
Okay. All right.
Excuse me. I have a question to ask. Did you get some metric to quantify how the load balancing is really working with your algorithm? Did you get some
no.
compare?
No, we
algorithm in accelerating the difference in active and reactive power to go quickly to zero.
No, we did not, but that would definitely be an interesting route to pursue. I mean, I think it's definitely something we should look into.
Any questions in the online audience? Once, twice. Any other questions in Illinois? Okay, interesting work. Best of luck at the NDSS presentation. Let's thank the speaker.
Thank you.